Assalamu alaikum wa rahmatullahi wa barakatuhu. Friends, welcome back to my channel. This is our fourth video on this regulated power supply. In video number 1336, we created voltage regulator from this power supply. 1336A, we created current control section. In last 1336B, that is third part, we connected BL02 voltmeter, ampere meter, watt meter. If I will adjust voltage from here, it is adjusting the voltage. If I adjust current, it is controlling current. And now we need output voltage protection. Why we need output over voltage protection? Let's suppose I created this power supply and I adjusted it to provide 3.3 volts. If I will connect this power supply to any charged capacitor, or there maybe any inductor that is providing high voltage spikes, or by mistake I connect the output of this power supply to any high voltage section, that time this power supply will damage. So we need a DC rail protection to protect this power supply. Or there is another scenario. If this power supply gets damaged, I want to test any circuit that is 3.3 volt operated. And if this power supply is providing output 28 volt, in that case, if I will connect this power supply 28 volt output, that is maybe regulation failure or anything wrong here. In that case, we will damage the next circuit. So there must be a vigilant circuit that will monitor the output voltage. In that case, we need over voltage protection. We will create a interlock circuit. Anytime if the voltage will increase, then rated voltage, we can say approximately 10%, that is called output swelling or line voltage swelling. So how much swelling we will allow? If 12 volt power supply, 10% swelling is allowed. 12 plus 10%, 13.2 volt. We need 12 volt from this power supply, but due to any error, if the voltage on output terminal will exceed than 13.2 volt, in that condition, this power supply output must be terminated. It must be disconnected. How we will create it? This is output line. We will connect a relay here. That will be connected all the time. We will use common point and NC points of a relay. We have 5 points of this relay. Common, normally closed, and this point is normally open point. Normally we will connect regulated output here at common point at this point, and we will take output from here. In any case, if the output will become high, this relay will disconnect the output power. We will control its coil. It is 12 volt operated. This line is power supply regulated output from 0 volt to 28 volt. Any voltage value that will come at common points that will go out from the normally closed points. But we are controlling its relay. Its relay will be controlled by another relay, and that relay will be controlled by a comparator IC LM339. I will use LM339. We can use Crowbar circuit, we can use any SCR, zener diode to trick the SCR. But in my case, that is much safer circuit. We will use another relay, two relay combination to make it self-locked. Once the output is touched to high voltage or there is any fault, until otherwise we reset the circuit, this relay will disconnect the power, output power. So next circuit will remain safe. I will use another relay. In normal case, that relay will remain off. In any condition, if this relay will turn on, here I will apply 12 volt positive. If this relay will turn on, that time it will provide voltage to this relay. Now we need to create an interlock. We will connect a freewheeling diode 1N4007 here. The same way one diode here. This end will be connected to positive voltage 12 volt. Now we need to connect a transistor here. I will use 2SC945 or any signal transistor that can drive this relay winding. Any NPN transistor. Emitter will be grounded. Now we need a control signal. When this relay will be triggered, it will turn off this NC point and it will close this NO point. That time this point will be connected back, looped back to its base using 5.1 K resistor. Anytime if this relay is triggered, these 12 volts will keep it locked. Walaikum salam, Turkey. Walaikum salam wa rahmatullahi wa barakatuh. Okay, now we need a comparator. To use this comparator, we will take this reference voltage because our reference will remain varying all the time. We will take this reference voltage from this setting, that is coarse adjustment and fine voltage adjustment, that are these potentiometers. We will connect this signal to inverting input, that is voltage setting. Here is a very technical point, how to program this comparator. It is a very simple technique. Normally, we are adjusting any voltage value from here. That value is regulated from this circuit and we are taking output from this capacitor. The same output voltage from here, from this feedback network, that is 15K and 10K, two resistors from the output terminal. That voltage are provided to this voltage divider network, and these are looped back to LM324 inverting input. We provide voltage setting to non-inverting and we receive feedback at inverting input. So it will regulate the voltage. Now we need overvoltage protection to determine this node. We will provide two resistors, this resistor, and we will take output from this point. We will feed it to non-inverting input of LM339. When we are using comparator, its output is open collector. We will connect a resistor here, pull up resistor 5.1K with 12 volts. Now here we need a base biasing resistor 5K1, 5.1K, 5K1. Okay, now we are combining two signals here, one signal from this side, second signal from this side. We will use 1N4148 diode here and 1N4148 diode here. So this signal will not reach to this side and this signal will not reach to this side. So it is one-way conductor. How to determine the resistor values here? We need a voltage divider network, positive out. Now we need to verify the signal value. Thank you, brother. Thank you for your valuable comment. Now we need to determine the signal value that will reach at inverting input. That is our reference signal. Very simple technique. When we are using linear circuits, operational amplifier, comparator, it's very simple. Common. What is the supply voltage for biasing up this circuit? It is 10.79. 11 volt. When I will adjust voltage, first I will set current to 0. Okay. Now this is our signal input for this IC LM324. When I will adjust voltage setting, amplitude of maximum signal is 10.96, 11 volt. So this signal will 0 volt to 11 volt DC. We need feedback. When we are calculating line swell for overvoltage protection, we have two conditions here now. We are designing overvoltage protection for a power supply. We have reference from this voltage setting knob because we will provide a tolerance to this voltage value. Our signal is 0 volt to 11 volt and our output is 0 volt to 28 volt. We have two conditions now. Input signal is reference signal is 0 to 11 volt, output signal is 0 to 28 volt. We need to map this signal. We need to plot this signal with a ratio that when we have 28 volt, this voltage divider network will provide 11 volt. So we need to calculate the resistor values. Very simple. Output 28 volt. We will consider the highest range. When we have 28 volt, let's suppose I want to design it at 1 milliampere. What is the ratio between this? We are creating overvoltage protection, but we will design it with negative reference. We will calculate 10% in minus sign. For example, at 28 volt, we need 5% minus 28 multiply 0.5, 26.6. 12 minus 12 multiply with 0.1, 10 point. Okay, 10% is good because we are using linear power supply. 10% will remain good. I have 11 volt signal. Yes, that's a good technique. We have 11 volt reference signal. We need 10% less signal at input pin. 11 minus 11 multiply with 0.1, that is 10%, 9.9 volt. When we have full setting of this potentiometer at 28 volt output, we need 10 volt, 9.9 volt at this pin. So we need to design our resistor network here. That means when 28 volt, I need 9.9 volt here or 10 volt. Okay, 10 volt, that's good. 10 volt here, remaining 18 volt will here. When we have 28 volt output, 10 volt will reach to this IC, this pin. In that case, it will remain off. At 28 volt nominal output, this circuit will remain off. In case the 28 volt power supply will increase, we have 10% margin. Here we have now 10 volt. When 28 volt power supply will increase 10%, 15%, that time this signal will also increase. When it will increase, it will become slightly higher than our reference signal, that is our required value. If real output is higher than our required output, let's suppose I connected to any 400 volt charge capacitor, that voltage will enter in our circuit, that will damage our power supply. To protect this power supply from external voltage, or we need to protect other circuits from failure of this power supply, this circuit will immediately disconnect load from this power supply. Now, if I want to take a simple ratio at 1 milliampere, we need 28 divided by the current value. So 28k resistor. For 10 volt, we need 10k resistor. And here we will need 18k resistor. Simple Ohm's law. So I will use two resistors, 10k, 18k. I have two resistors. This one is 10k and it is 18k. This resistor is RKM code. 18k, I will use 18k and 10k, two resistors. Now I need these two resistors to be connected at output terminal. K resistor will at lower side, at ground side. When I have 27.97, that means 28 volt, On this center node, I have 9.88 volt. That's nice. And our reference signal is now 11 volt. Fantastic. That's what we need. We said we have 11 volt reference here and we need approximately 9.9 volt, 10 volt at this pin. Now we have 1 volt headroom at reference and feedback. Now we will connect this signal to this IC non-inverting pin. LM339 datasheet. LM339, pin number 3 is VCC. Pin number 7. Pin number 7 is non-inverting input. Inverting input is pin number 6. VCC pin number 3, ground or return path at pin number 12. That is this IC. Now we will connect positive voltage to pin number 3. Because its VCC pin is pin number 3. pin number 3. I am not using PCB or any project board. Here we will find exactly that clear concept when we are designing any circuit. Here is exactly the same concept. Pin number 3 is positive 12 volt. Pin number 12 is ground. We will connect 5.1 kilo ohm resistor as a pull-up resistor at VCC and pin number 1 because pin number 1 is output. Pin number 1 output. Pin 6 pin 6 inverting input. It is 5K. With tolerance it is good. I will connect this resistor between pin number 3 and pin number 1. Now we will connect return path, pin number 12 to the ground side. So here is 12, 13, 14, this pin. It is pin number 12. You can use comparator circuit, comparator IC for your any circuit where you are designing any comparable values. Here is our return path. I connected positive ground. Ground at pin number 12, positive voltage at pin number 3. Now this IC is powered up. Now we need to inject a reference signal, that is voltage value from this IC that we are feeding to this operational amplifier for voltage requirement. That is pin number 6. These linear ICs are very interesting. So in this design, I am using one LM324 for current and voltage adjustment. And now I will use this LM339 to protect the circuit from overvoltage, undervoltage, and we will also use a heat sensor, any NTC, to sense the heatsink temperature. And we will turn on fan. And after that, after this prototype, we will design this circuit on a PCB. And then I will share its circuit diagram. Now we provided a reference signal. Now we need feedback signal from this resistor network, that is 18K and 10K. And then we will connect relays. If you are enjoying this video, if the live stream is good, hit the like button. Now our feedback is ready. We will connect at pin number 7. When you want to compare any signal, we need a reference signal. You can create your fixed value reference, or you can create a variable reference. In our case, our reference voltage are varying all the time. Now in this UPC 339, LM339, whatsoever, KA339, it is available with different numbers. Here I connected 5.1K pull-up resistor because in 339, 239, 139, whatsoever, any comparator, in this series, the output is open collector output. So we need pull-up resistor that I connected between positive 12 volt and return path. We will use this relay now. These are relay windings, the output 2 terminals. Center pin is common. These 2 points, 73 ohm resistor. 72, 73 ohm resistor. We will use C945 transistor as a low side driver here. Emitter will be connected to ground. Positive voltage will reach to this relay winding, 12 volt, which we are using here, that are to be interlocked. First relay winding side will be connected to positive side, and second pin, winding second pin, will be connected to collector of this C945 transistor. To SC945 pin out. Pin 1 emitter, pin 2 collector, pin 3 base. Center pin is collector. Center pin is collector. Collector will be connected to the winding. Emitter, collector, base. Emitter will be connected to ground. We connected emitter to the ground, collector to the winding. Here we will connect at base pin, we will connect resistor 5.1K, and we need C94 and we need 1N4148 diode. I always try to use old components, second-hand parts. Rarely I purchase new components. If you have a scrap stock, that's much better. Yes, this 1N4148 diode is good. It is one-way conductor. We are protecting the circuit from any unexpected load. Cathode of this resistor is connected to base. And we will also connect the second diode at the same point. Both cathodes will reach at same point. So this transistor will be operated by two different signals. One signal from this comparator and second signal, that is interlock signal. Anytime if this transistor is triggered, either for milliseconds, immediately this relay will turn on this transistor for all the time, so that we need to check the circuit, we need to turn off power supply to reset it. And maybe in upcoming session I will add turn output power control to turn on, turn off, so that we can control the circuit. Now I connected this resistor. This resistor will reach to operate this comparator pin number 1, that is drive signal. Resistor this end will reach to pin number 1 of this IC. So anytime if the output voltage are increased, it will provide trigger signal. For this transistor, yes, we have now this trigger signal. I need 12 volts at winding this end, and we will connect to the second wire, that is common point, because we are controlling this 12 volt. So this relay have no concern with the output voltage. It will be controlled by the biasing supply. I will connect common wire and winding one end to the same point. This point, it will reach to positive 12 volt. When all protections are connected, that time I will connect it to a circuit, a box, and we will install this panel meter. Now I need 1N4007 diode as a freewheeling diode. Cathode will be connected to positive supply. It is a reverse polarity diode. Now when this relay is off, We have common pin, we have 11 volt that are VCC voltage of that circuit, and the same 12 11 volt are reaching at NC point, normally closed point, and this point is disconnected. Now let's test this circuit. Now we have 27 volt. I will set it to, I set 23 volt. I adjusted this circuit to take 26 volt. Now we have 9.2 volt at reference pin, and we have 8.1 volt at feedback pin. In case our this circuit is now facing any problem, let me connect this resistor so it will make interlock. 5.1k resistor here. Once this relay will turn on, it will interlock, it will provide 12 volt to the transistor. We have 23 volt output now. If I remove this circuit, now if I will disconnect this circuit from here, or the second situation, if I connect this transistor, emitter and collector together, voltage just increased to 28 volt, and now this relay is turned on. Now we have output on this point. This relay is now interlocked. Now we need to disconnect power, turn off power supply, then it will release that interlock. The power supply increased for the time and then recovered back, but this interlock will not release power supply. We can see now it is open circuit, but we are receiving that voltage at this point that is not connected. Let me connect another time jumper, this transistor, emitter and collector. Once voltage increased, now it is locked. So our interlock is working nicely. Anytime if there is error, there is a slightly voltage spike, it will protect this power supply from any external interference. Let's connect the final stage relay. In final stage relay, we said winding one end will be connected to ground, and there will a freewheeling diode between the relay winding. I connected a diode here. Now this cathode side will be connected to positive voltage, and that positive voltage will reach from this interlock pin that is this point, and this winding end will be connected to ground. This side, anode side, will connect it to emitter pin. And this is now our final test point. This will reach to this relay, that is NO point, normally open point. When there is a trigger, this relay will make interlock by the help of transistor and its resistor network. Yes, there is something. Yes, here is some error. First, I will remove this interlock. Okay, we have some error here. No problem, I will fix it. Now the output is there. What happened? Yes, there is some error, I think. Why it is being operated? Why it is turning on? Yes, now. Okay, now. We have something wrong here. $10.98. 10.98. That are good. This comparator is working nice. 6.3 volt, 5.5 volt, 3.9 volts. That are reference voltage. Yes, yes, there is one error. That is not error. That is not error. That is not an error. Yes, now I detected the problem. 8 volt, 8 volt reference, 0.6 volt. Why 0.6 volt? Yes, I am decreasing the voltage very quickly. Yes, now it's interlocked. There is something wrong here. This emitter, and here is positive voltage. I will connect it. I think I have this issue. We will continue in upcoming session. I will find the issue. Where is the problem? Why it is making interlock at mid level? Ideally, reference voltage, feedback, and then I will continue with our complete design. Now I need to study it, why it is creating this conflict. If I disconnect feedback, yes, now it's clear. I have some issue. Meter, this positive voltage, we have some issue here in this section. These voltage are looping back to base. Positive voltage and same positive voltage are here. The configuration is looking good. Yes, now feedback. Voltage are good now, increasing. Current is being controlled. Feedback voltage are increasing. And this time, feedback 2 volt. Reference is good. Now, I need to connect output here to provide in the second side noise to the load. Yes, I think our problem solved because these capacitors were making problem. Yes. Because when I was decreasing the voltage, the output capacitor bank is still charged. That was creating high voltage interrupt, that there are more voltage in the output side. I think there is no issue. Now we will test it. Let's check it now. Friends, I have some issue in the circuit in this feedback network interlock. I will study it again and then we will continue. Thanks for joining. Assalamu alaikum wa rahmatullahi wa barakatuh.